Another polynomial. So let's go ahead and identify all intercepts, all local extrema, and all inflection points. But let's see how far we can go with just our basic tools of algebra from pre-calculus. So to find intercepts, I certainly need to come in here factor. And let's see, excuse me. Clearly, this does not factor by grouping, so I have to use the rational root theorem. And in using the rational root theorem, the only rational zeros are going to be of the form P over Q, where P divides evenly into the constant term. Q divides evenly into the leading coefficient. So I have to admit I've got a lot of choices. Let's try 2. And instead of using polynomial long division, if you don't mind, I'm just going to use synthetic division as a shortcut. Oh, look at that. It works quite nicely. What that really means is that this third degree polynomial factors quite nicely into an x minus that 0 times a trinomial whose coefficients are here. Now, I did not expect this when I created this question, but it appears this trinomial factors quite nicely. I got a little lucky. I really did not mean for that to happen. So 10 is at my 5 and my 2. And let's see, that'll be positive, that'll be negative. Now look what that really tells me. It tells me that I've got an x-intercept. At 2, 0, and at negative 5/2, 0. Now, in building my sign graph, plugging a value in for x over here, everything's positive. That's a 0 of a linear factor raised to even power. It does not act as a toggle switch. That's 0 of a linear factor raised to non power. It does act as a toggle switch. So I live below the x-axis to the left of the x-intercept, and above between here and here, and above from here to there. So it looks to me like my polynomial has to behave something like this. Now, I gotta confess, I pulled a fast one. I don't know that I locally max out to the left of the y-axis. I might locally max out to the right. I don't know yet. But that'll come up when I compute the first derivative function. I do, however, know that I've got an x-intercept located, excuse me. I do know that I have a y-intercept located here. So next on my list, let's differentiate. And build a sign graph. But remember, this is a sign graph of y prime. What it tells me about the original function y is that it changed an increase and decrease and increasing as such. And so I guess I immediately know that I locally max out at a point whose x-coordinate is -1. I'll leave the y-coordinate for you. And I locally min out as I knew at that x-intercept. Now, as far as inflection points, it looks to me like I'm only going to have one somewhere right around there. And to find it, I'll differentiate one more time. Build a sign graph. But that's a sign graph for the second derivative function. What it tells me about the original function is that it changed from concave down to concave up about an x value of +1/2. So that inflection point right there has an x-coordinate 1/2. only for you to plug that in for x here to find the corresponding y value. So, like my last example, it's almost as if I just added fine detail to the graph of this Pauli function beyond what I was able to do in studying basic pre-calculus.